Welcome, folks that are online. So my name is Peter. I'm one of the core developers of Napari. I work in research IT at the Jackson Laboratory. I support people using our high-performance computing cluster and general computing resources for their open source bioimaging pipelines and things like that, which includes actually more QPath and subprofiler than Napari, but that's how it is. Um, Today's workshop is going to focus on using Jupyter notebooks and Napari for exploratory image analysis. This is something that when I was still doing science, I found very valuable, and it's actually what got me into Napari in the first place. Um, it's going to be pretty relaxed. It's a little late here, so some folks maybe on the East Coast are tired. For other folks, if it's in the morning, maybe are just waking up with coffee. So if you have any questions, just feel free to unmute yourself and ask, or use the X if you want me to stop, or if something is unclear. I'm going to share my screen. Actually, before I do that, so can I get so basically the only thing the thing that you need to be able to do this workshop is a installation of Napari and Jupyter in the same virtual environment. I'm not sure how many folks got that information or were able to do that. Can I get a reaction? Can I get the green check mark if you have Napari and Jupyter and you want to follow along and basically code along with me? And can I get a red X if you don't have a virtual environment, don't know what I'm even talking about? Okay, so we have a mix. All right. All right. We'll make this work then. Okay, so there's a shortcut that we can do, and so hopefully this works. And yeah, so let me share my screen, and then hopefully we can get you all set up quickly to be able to do this workshop in a way that should work, but maybe not be the ultimately ideal way. But then you'll find out whether you like Napari or not, and whether you care about this, and then you can figure out better ways of doing it in the future. So let's clear the feedback, and I'm going to share my screen. I want to share this screen. Okay. Um, I would like to see. Can someone just do like a regular thumbs up a reaction or something if you can actually see me sharing a screen that has the exploratory data analysis webpage open? Cool. Awesome. Thanks. Just wanted to make sure that this works. So I will put this in the chat one more time. These are the materials. And just to give you an overview of the materials, there is a getting started section, which covers installing Napari, and we'll come back to this in a moment. There is also instructions for how to get started with JupyterLab, which is what I'm going to use. There is a section on how to download the notebooks if you want the solved notebooks, either for yourself now or afterwards. And then there is also an alternative for doing this in the cloud. This is pretty slow, so this may not be the best option, but it is an option. And so, in fact, I'm going to quickly activate that because it's slow to spin up. And if I activate it, it'll be faster for everybody else. So that's one aspect, and we're going to get back to this installation thing in just one moment. And then I've prepared a notebook and this is the fully solved version, so you can just follow along in the web browser, that we are going to work through together, interactive analysis with Napari. And then there is a second one that is very similar, but slightly different if you want to be able to follow along with one on your own. This one maybe is slightly more advanced. And then there is an optional intermediate one that is linked to the second one. So if you do the second notebook on your own time and you want to take it a step further, then that would be this extra notebook here. So our goal is going to be to work our way through this notebook. And so if you don't have Napari, so let's see here. Let me find the reactions again. Okay, cool. So the instructions and the easiest way that I'm prepared to help you install Napari from scratch would be using conda. Can I get a green check mark if you have conda installed? And a red X if you have no idea what conda is. Oh, cool. We actually have a bunch of green check marks. Okay, cool. So then we actually can skip the probably Ved. I didn't see a reaction from you. Do you either do you know what conda is? Do you have conda? If can you say a green check mark or a red X? Or do you have another way of installing Python things like a Python virtual environment? Let me check the chat. Yeah, but not on my. Okay. All right. Okay. So, Ved, I think the best thing for you to do would be right. But if you don't have it, if you don't have a way to work with Python on your current laptop, then maybe the best thing for you to do, Ved, would be to follow this tip. You could install the Napari bundled application for your operating system. And then we have a plugin that'll allow you to access Jupyter from the party. So you won't have to set up a Python environment, install Python, or anything like that. And then everybody else I see has a green check mark. So they have Conda. And so for the folks that have Conda, you can just skip all the way down to the environment, which is literally just installing Napari, PyQt, and JupyterLab. So if you have Conda and you can run this command, then that'll get you set up with everything that you need. And then if you really want to, you could clone this repository or the in the repository, if you click on the GitHub link here, you can also access there's an environment.yaml file if you really want to do that. And you can also download the repo as a zip in order to access the notebooks. And then Binder is still spinning up, so another minute or two, and this should actually be doable using Binder. So we'll see if that actually gets kick-started or not. So those would be your options. Either if you have Conda or some other way of installing a Napari, PyQt, and JupyterLab, then you can do that. If you don't have access to Python, then to follow the instructions here to install the bundled application and the Napari workshop browser. And I can demo how that would work in Napari. I'm going to clear the responses. So I'm happy to answer any questions if folks are trying to work through this. Otherwise, you can put up the green tick mark when you have Napari and JupyterLab installed, whether that's through Conda or installed using the bundled app as I'm trying to launch. And then we'll see if Binder actually launches. It's still working. Unfortunately, this takes quite a bit of time to spin up. And if you have any questions or problems, just unmute yourself and we'll just work through it. This launch time for Napari is not representative. I'm on my work laptop, which has a whole bunch of security software, and every binary gets scanned and the code gets analyzed. And so, unfortunately, this security software makes it very slow to interact with things that are not in a web browser, which is one of the reasons that I'm going to be showing you how to use Jupyter. Where's the? I've lost the chat window. Okay, there's the chat window. Cool. All right. And then if you don't, if getting it installed and you don't want to install it, that's fine. You can, well, let's see if this Binder is working. No, still working. You can just, everything is solved in the notebook, so you can just basically see and follow along with what I'm doing. Also an option. All right. So for this workshop browser, I'll just show you real quick. When Napari opens, there is the install plugins, and here you would type workshop, and it's the first plugin. So you would just install this workshop browser plugin, and then you need to copy this link. So you would just copy link and then paste it into the plugin once it's done installing. I'm not going to install the plugin because I don't want to change my environment that I'm using right here. I don't think it should affect anything, but it does install its own Jupyter, and I already have Jupyter installed, so I don't want to. I don't want to mess with a good thing. If anyone is having any difficulties or has a question, please speak up, or just show me the red X if you're having a problem, and we can use chat or whatever to try to resolve it. See if binder's finished. Oh, it's almost done. Cool. So that will be an option as well. All right. So how are folks doing? Are y'all still trying to install the virtual environment? If you have conda, are you all still trying to do that? Still installing? Okay. All right. So Binder has launched. So if anyone wants to try to use the cloud platform, you can certainly do that. So you would need to go to the notebook. You need to go to this page, and I'll put it in the chat. Um, If anyone wants to use the cloud platform, then you would go to this web page and then click the binder button here in the top, the rocket. And that will launch this interface, which is exactly the same as what I'm going to be doing. So if you're having trouble with the installation, or you just want to give up on that, you can try using the cloud platform. Everything that we're going to be doing isn't going to be super like resource intensive, and I've tested it in the cloud platform. It's not the best experience, but it's better than nothing. So that's an option. And if you're just ready to move on and to get started with the material, and you're either going to figure out the install or you're going to follow along, then just put up the green check mark, and that way we'll see how we're doing. But if you're still installing, and then please go ahead, and if you have any questions or problems, just speak up or use chat. I got a bunch of green check marks. Cool. Looks like everybody put up the green check mark. Laszlo, I saw a green check mark from you for a moment, but it's down now. So do you need another minute? Are you almost? Oh, you're done. Okay, cool. All right. So I'm gonna clear that, and we're gonna get started. So I'm gonna close the binder. I mean, actually, I might as well um, if you are interested in using the binder platform, you would click the plus to get to the launcher, and then you would just activate the desktop feature. Um, and that way your Napari will show up in this desktop window, and then Jupyter, which is what I'm going to be doing, is going to be here instead of showing up in your local desktop. Um, so I'm going to just drag that off to the side and get it out of the way. Maybe I'll just do this. And then I'm going to get started with a local Jupyter Hub. So you can see that I have the environment activated. It's the environment from the instructions. and I'm going to type JupyterLab in order to start Jupyter here in this environment. And then I have my Jupyter interface. I'm going to make this a little bigger. Hopefully that is big enough. And again, we're going to be walking through this notebook, the interactive analysis. And so you can follow along in your own web browser if the screen share isn't great. So I'm going to be I'm going to do the coding in an empty notebook, and you can do the same, or you can copy paste the code cells if you would like. You can do whichever works. So we're going to get started. And so now I have Jupyter running here in a new notebook, and I'm going to import Napari. It's the first thing that we need to do. We need to make sure that we have Napari imported such that we can, and I already forgot what is the command for a new code cell. Oh, why is that wrong? There we go. So once we have Napari imported, we can start to use some of the Napari features. And so the first thing we're going to do is we're going to open a Napari viewer. And I'm calling this viewer. That's kind of a handy default. We use that a lot in some of the examples and things. And so this first run of it might take a moment, but hopefully it doesn't take too long. And then you'll have a Napari window that spawns on your desktop. If you're using the binder, then it will spawn in that extra tab. But also, if you're using binder, I should have mentioned this, you need to copy this code cell and execute that as well. So can I get a green check mark if you either have a Napari window that has opened, or if you're just ready to move on because you're following along? Cool. Excellent. Okay. So the next thing that I'm going to show you is something that it took me a while to learn, but I find it actually to be one of the most useful things when doing exploratory data analysis like this. The whole idea of a Jupyter notebook is that you can toggle between the markdown view and the let me see here. Of course, I am not able to do the thing right now. Where did it go? Here we go. Between the markdown view and the code view. So in the markdown view, you can write yourself some information. So you could say, learning Napari, I will take notes on my analysis. And so this way you can take notes and give yourself some information as you're walking through an analysis protocol. So this is one of the nice things about Jupyter Notebooks is that you can write basically nicely formatted text alongside your code. So that's number one. And then the other thing that I think is really handy, and if you want, you can just copy paste the code cell. It's right here, this nbscreenshot. But so you would go from napari.utils, import nb screenshot. And so what this function does is it will capture the viewer that you have open here and basically put a screenshot of it into the notebook so that you can document what you actually see. And so let's see how that works. NB screenshot. Actually, tab should work here. So NB screenshot. Yep. And then viewer. Viewer is the name of the viewer we want to capture, which is this one. And so if you execute that code cell, you will get, in a moment, boom, you get an image of the code of the viewer in the same state as it is over here. And so I found when I was still doing science, I found this to be very useful because I could basically iterate, write myself notes, explore different parameters, different properties, like some parameter of a filter, and then encapsulate screenshots of the output of how it looked in Napari as I went along. And so I could develop a workflow I could test the pipeline. I could do those kinds of things interactively using Napari and Jupyter, but then I could save sort of the intermediate results along the way. And frequently those became figures in papers or were used in lectures or lab notes or whatever was handy. So this NB screenshot, I think, is a real is a very handy thing to keep in mind. And then I want to add one other thing is that you can do NB screenshot viewer, and then you could say canvas only equals true, and then you will get a copy of just the canvas, which right now is black. We don't have anything showing, but you could get a copy of the canvas. The next thing I want to show you is that at the end of the day, Napari is happy to display anything that is basically an array. So an array of numbers is basically a grid. A 1D array is simply a list of numbers, say 1, 2, 3, 4, 5. That is a 1D array. A 2D array is sort of like what you see here. So each pixel on the screen has some sort of value. And then, of course, a 3D array, 4D array, so on and so forth. So depending on the kind of files you're working with, you're using proprietary microscope files, you might be using any kind of different file types and things. How you load them essentially into an array is up to you, and Napari is very agnostic about that. There's plenty of plugins for Napari that'll allow you to read different formats. For my work and the people that work at JAX, we tend to use TIFF file the most. It opens all the TIFF-like files, and most of the images that we work with are TIFF-like. And so that's the example I'm using here. You could download this data file. It's actually in the repository. There is a data resources folder, but this is just an example. So if you had a TIFF, you could use TIFF file, which has the imread method, and then you could load that TIFF into a variable, and then you could show that. For the purposes of this workshop, we're going to use some sample data from scikit-image. This ensures that everybody has it and that there's no issues with downloading. So let's load that data from scikit-image.data, import cells 3D, and then image data equals cells 3D. And so we're going to call this imported function, and then we can see what image data is. So this might take a moment. It might need to download. Hopefully it doesn't take too long. But then you see the shape of this array of numbers. And so this is actually a 4D array. So it's the spatial dimensions are 256 by 256. There is actually 2 channels in this image. And then it is a Z-stack in this case, which has 60 slices. And so for what we're going to be doing in this notebook, we only care about the one of these channels, the nuclei. So I'm going to grab that channel. So I'm going to call this variable nuclei. And so I'm going to just use indexing image data. That's the array. This is the NumPy array. And so now I can index into it. I want all of the Z slices. So I use a colon to indicate that. I want just the second channel. And so Python starts 0 and then 1. So the second channel is the channel index 1. And then I want all of the Y values, and I want all of the X values. And so if I do that and get the shape, I should get an array that is just a 3D array, 60 slices by Y and by X. And then we can add that array to the viewer. So I will use the add image method, and I will add nuclei to the viewer. This is the name of the array. So that's what I'm passing here. And I'm going to make it color map. I'm going to give it color map green. I will ask Napari to render the intensities in different shades of green. And so I will execute that. And then I have it here in my Napari window. So you see, I executed code here in the notebook, and the response is over here in the in the viewer. Can I get a green check mark if you either have the nuclei in your viewer and you can view them, or if you're ready to move on to the next to continue with the example? You have something loaded anyway? Cool. And so now you have some options. So for example, you can play around with the contrast limits, right? You can do whatever you want in order to adjust how this looks. You can change some settings here. You can also change to say a 3D look. And so I will do that just for the sake of this example. And then I will execute our, obviously I could write some markdown here for myself as a comment, but I won't because I'm lazy. But I will execute nbscreenshot viewer just to record the the image that I have here in napari. And I think I put it in the materials. There's a bunch of other things that you could do. So for example, you could set the scale of the layer. So you could assign the spacing. So this is essentially, in this case, this would be microns per pixel, but you can assign the spacing. You can do all sorts of different things to manipulate the layers. I encourage you to check out some of the tutorials and things that are on the on napari.org. But what we're going to do here is we're going to just keep going with this paradigm of working in the Jupyter Notebook and then seeing some intermediate steps. I have a bunch of libraries here that I'm going to use and import from. Mostly you see from scikit-image. We're going to use the features. We're going to use some filters. We're going to make some measurements, and we're going to do a couple other things here. And so just to save on time and typing, I'm going to, because I already typed this once, I'm going to copy and paste this code cell, and I encourage all of you to do the same. And again, remember, if you have any questions, need me to stop, just unmute yourself and say something, or put up the red X. So I'm just going to paste all of those imports such that we get them all out of the way. Obviously, we could have just imported scikit-image, and then we could access these using scikit-image.util, scikit-image.segmentation. But I think it's a little bit simpler to do it this way. And so that's what we're going to do. So if our goal is to segment this 3D image, then what we want is every one of these nuclei to be have its own either outlined, or basically all of the pixels that are part of this nuclei to have their own index so we can find them, and then all of the pixels that are in this nuclei be indexed with their own index, and so on and so forth. So that's basically the segmentation task. And if you were watching when I was playing with the contrast limits, you may be already able to see that there is some background to this image, and then the nuclei are pretty intensely green. And so one simple way to segment things in bioimaging is to use thresholding. So that's what we're going to do here. But obviously, you could use your method of choice to do the segmenting, and you could explore it using the same process that we're doing here. But I'm going to use a segmentation using thresholding. So let's do the most naive approach, which is just to do a simple automated threshold on this image and see how far, see what that looks like. And I think this is where Napari really shines. So we can do a couple different things. So let's literally do the simplest case. So let's do foreground. I have no idea. I am mousing over. I don't know if you can see down here. Actually, I can make it visible, more visible. Sorry. Appearance. I'm going to just make the font here bigger. Okay. And so look down here in the corner. As I'm mousing around the image, you will see some values. So like, for example, here it's 7,000. And as I mouse over here, we see 24,000. Okay. So the first thing we're going to do, we're going to take the super naive approach, and we're going to say the foreground pixels are equal to the nuclei pixels greater than or equal to 7,000. And so this is sort of the simplest way to threshold. I basically want all of the pixels that are greater than value of 7,000. And honestly, I don't know exactly what this is going to look like, but I can take a look in Napari. So I could say add labels. So this time we're going to use a labels layer. You'll see in a moment why. Foreground. So I want the foreground. Um, and so I'm going to give this layer a name, and we're going to say manual. Okay. And so now we have our manual segmentation. And you could see that, okay, I mean, if we take a look, we can play around with this and we can see that, you know what, like, that's actually not that bad, but it's a little noisy, right? So it doesn't look great. And particularly when we see in 3D, we see that there is quite a lot of noise. So this manual approach, we could tune this, right? We could now use the information that we have here. We could say, well, let's take a look at some of this noise that's here. Let's see what the values are. And then we could, I'm sorry, here, the values here are 8,000. So maybe we need to bring up the threshold. But instead of doing that, why don't we use an automated threshold? And we see that there is a fair amount of noise. So why don't we use a classic method and apply a little bit of blur, and that way we can eliminate some of the noise. And so there's a lot of different filters that you can use, and I link to a bunch of them here. So there's a bunch of filters. You can use a Gaussian, a median is very popular. And if you follow these links, you can get to the scikit-image documentation and you can explore all the different filters that are available. But I'm gonna use Gaussian because it's simple. And so let's use a Gaussian filter. And the goal of this Gaussian filter is to eliminate some of that noise and to make it easier to identify the objects versus the background. So in order to apply a Gaussian filter, we will take the filter from the filters that we imported here. And tab autocomplete is really nice for things like Gaussian. And then what do we want to filter? We want to filter the original array nuclei. So we're going to filter that. And then we need to provide the radius that we're going to filter over. I don't know. I think you can see actually in behind my materials that I use the sigma of 3. You can pick whatever value you want. I'll try maybe, I don't know, 1. I don't know what that, no, that's probably silly. 1.5. I don't know. Just to be contrarian. And then I'm going to use this preserve range keyword argument true, which will basically, by default, what scikit-image tends to do is it tends to convert outputs to be between 0 and 1. But in this case, this blurred data, I want to keep the original range of the data. So you can see that the numbers here are like in the thousands. And so I want to preserve that. So I'm going to apply this blur with the Gaussian. And then let's take a look at it. So viewer dot add image blur. Let's see what it looks like. And again, this is the nice thing about the one thing I really like about Napari is that I can take a look. So how is this blur look? Yeah, it really actually did. We got rid of quite a lot of that salt and pepper, right? The edges here are maybe a little smoothed out. Let's see here. Did I see something in the chat? No. Okay. And if we use the 3D view, I'm just going to disable that. It's definitely the signal here is the signal to noise here is going to be a little bit better. So this looks pretty encouraging. So even with this sigma of 1.5. So I'm going to now use this blurred layer for the thresholding. And I'm going to use an automated threshold again from scikit-image. So I'm just going to trash this blur layer because we don't need it for anything. So delete. And then let's get back to let's try the thresholding. So now we're going to say foreground equals. So we're interested in using thresholding. We're going to threshold the blur data. So that's this variable blur. And we're going to use greater than or equal to. And then we're going to apply a filter. And we're going to use a threshold. And so you can see there is a bunch of different thresholds that you can automated thresholds. So you may be familiar with Otsu or Lee or local. Again, I provide you the links. You can pick whichever one you want. Otsu is really popular. I don't know. I'll use Lee just as a different one. Uh, and the data I want to threshold is the blur, right? The blurred data is the one that I want to threshold because this is the data, the array that has some of the noise removed. So we have the threshold, and then we can add that to our viewer. And I'm going to give this a name, and this is going to be Lee. Good enough, Lee. And execute. And there we have it. So we can now compare the two, compare the two layers. So this is our blurred and automated threshold. Looks pretty decent. And then here is the non-blurred, naive, just manually picking a number. So, I mean, I think we could see pretty clearly that that we have a pretty big improvement here in terms of the overall segmentation. And if we go, we can take a look. But notice there are some holes, so there's some imperfections here. But overall, we don't see any of that noise. And again, we can compare. And the cool thing is that we could just rerun any one of these code cells, right? So we could go back here and we could enter a sigma of 3, right? Change to a sigma of 3. I'm gonna not add it to the viewer because I don't want to junk up the viewer. So if you use the hashtag, that's a comment. So I'm gonna just run this again with a sigma of 3, and then I'm going to run change the name here to Lee Gauss 3. And I can run that. And now I have the 2 layers, right? And so now I can compare how does Gaussian sigma of 3 look versus a sigma of 1.5. And so one thing I notice is that when I use a Gaussian sigma of 3, those holes get filled. But also I notice that there's some spillover. So notice how this is connecting in a much wider way versus the 1.5. Yeah. So this is the kind of trade-off. I can explore the influence of the parameters by playing with the values like that. So I think I'm gonna maybe stick with the go back to maybe I'll pick a middle value 2. That seems fine. And I'm gonna just delete both of these layers and the manual one. We don't need it anymore. And I will have let me just leave this as is. But actually, this would be a good place that we could leave ourselves. If we were doing we could do a comment here and we can give ourselves some information. So we could do the markdown Gaussian sigma affected holes in the nuclei, but also spill between 3, maybe 2. Okay, and then we can do nbscreenshot again to capture a representative image. And so let's do that as well. So we have that. So we have just done the simplest part, which is a relatively simple segmentation. But I think that hopefully you can see that by by playing around with the parameters in the notebook in an interactive fashion, but where these parameters are recorded, right? So if you go back to this notebook in 1 year, you'll see that you used a sigma of 2. You can leave yourself a comment and you could see why you picked a sigma of 2. So I think there's a lot of power in doing that. What questions do y'all have about what we have done thus far? Has everyone been able to play around and get a filtered or a segmented image where you have a labels layer and an image layer? So you have the mask on top of the image. Can I get a green check mark if you either have something like this in your viewer, whether you use Otsu or Lee or whatever, or if you're ready to go forward? If you're just skipping and want me to go forward, then you can also give me a green tick mark. Cool. And please, if you have any questions, just stop me and speak up. So the next thing that we're going to do, just continuing the theme of sort of trying to improve this and get to where we're going, we want each of these nuclei to have its own label. And right now we see that they are all labeled. Sorry, I can go here. We see that they all have the number 1. So the background is 0, but each of the nuclei is 1. So scikit-image provides. Let me just show you where this is in the materials. Scikit-image provides a number of different kind of operations called morphology operations that can be used to clean up once you have a binary mask, to try to either fill the holes or remove some noise, play around with that once you have a binary mask to try to really get the nuclei to be their own things. So we're going to try to remove we're going to try to improve this this a little bit. And so the first thing we're going to do, we can call this foreground processed. And so the first thing we're going to, again, we're using this morphology module from scikit-image. We can do a binary opening. So basically what opening is going to do is it's going to sort of like widen everything. And that's going to tend to close some holes. It's going to tend to get rid of some small pieces and fill in some small holes. And so we're going to run that on our, sorry, we should run that on our foreground, right? So we have the thresholded, the binary mask is called foreground. So here I made a mistake. This should be foreground. That's the actual binary mask. And if we want to see what kind of effect this had, we can do viewer, add labels, foreground, processed, autocomplete is your friend, and we should see. So in this case, you could see that if I toggle it off and on, it doesn't really seem like that actually did a whole lot. I suspect that what's happened is that we did a pretty good job of filtering. And so I think we already got rid of many of the kind of things that opening would handle for us. And so it looks like the opening actually isn't really doing anything, at least not as far as I can tell. So I'm just going to delete that layer and we will continue. So we can say foreground. I'm going to just overwrite the same variable because I don't care about this intermediate step. I've got a typo here. Again, autocomplete is your friend. Foreground processed equals morphology. And now we're going to get rid of small holes. So remove small holes. And this time I'm going to use this object that we already did the opening on. It didn't seem like it had a big effect, but we may as well use it since we already did it. And so the small holes, we need to think about basically what the threshold is of like what we want to get rid of. So in this case, scikit-image uses the keyword area, but it's in our case it's a volume because this is a function sorry, a method that can handle 3D data. And so what I'm gonna, these nuclei, if I just use my eyes, you know, if this is 256, they're like 50, maybe 60, 50, 60 pixels long. And so I'm going to consider a small hole basically 2 to the third power. Sorry, 20 to the third power. So anything under 20 to the third power, I'm going to consider a small hole. And again, you could play around with this parameter and to determine what is actually needed to get rid of the holes. But I think this seems pretty reasonable. I want something that's smaller than the smallest nuclei. And so where's the smallest one? I don't know. It might be, I think it might be this one. And this one here, it's like 88 to 130. So it's like 50 pixels across. So I think 20 seems reasonable. So let's run that. And then viewer.add labels foreground processed. So let's take a look at that and see if we made any progress. So here is our here's our hole, right? And we can see that there's the hole here. And then here's when we remove the hole, and it looks like the hole's been removed. So that's good. And then let's see if there's anything strange going on. Have we lost anything important? It doesn't look like it. It looks pretty good. So let's go to 3D mode. I always like to use 3D mode to sanity check things like this. And I think that looks pretty good. We do see that there are still these small objects, though. So we could get rid of those. We don't want to consider those as nuclei, right? So that's not a nucleus. That's probably something, I'm not sure what that is. But maybe it's some little bit of mitochondrial DNA or something like that. But we definitely want to probably get rid of that. So we could do the same thing that we just did, but instead of remove small holes, we can do remove small objects. So we will do foreground processed equals morphology, remove small, and again, we picked small objects this time. So we want to take this same array that we've already processed once. We're going to now process it a second time, and our goal is to get rid of these objects that are small, right? So again, I'm going to go to the 2D view, and I'm going to just mouse around, and there's one of the small objects. So the small objects appear maybe 5 pixels across, but we see that the smallest nuclei is like 50. So we need to provide this, we need to provide a size. And here, I don't know why it was area threshold for small holes, but it's minimum size in the small objects. It doesn't really make any sense to me. So I'm going to do 10 pixels cubed. So that should be a threshold to get rid of, make sure that we get rid of all these objects. So we should get rid of this, but we should keep this big one. That is my hypothesis anyway. And so let's do that. Viewer, add labels. And I'm going to just delete this other one. Actually, I can show you guys how to delete it programmatically. Viewer dot layers -1. That's the topmost. And then I should be able to just say pop. I think this should work. No, it doesn't work. Oh, interesting. Cool. Okay. So I'm not exactly sure how to programmatically remove. Oh, wait. Viewer dot layers. Remove. Maybe selected, something like that. No. Awesome. I'm not exactly sure how to delete. Oh, no, it worked. Okay, so remove selected work. Okay, so we can do it that way. And so now we can do viewer, add labels, and we can add our foreground processed. And so this is our new one, and now we expect to lose. Oh, there it is. We can see that this is no longer. And here's our original, and we see that we had this small object, and now that small object is gone. And if we go to 3D, we see that we lost these things on the corner. Actually, let's shuffle the labels so we get a different color. So you see here that we got these small objects here on the corner. We got this small one here. We got this clipped thing here. We got some other small objects. So this looks pretty good. I think we've done a pretty good job of cleaning these up. So I'm pretty happy with this foreground process. I think it's good enough for what we need. But we don't have we still see that many of these are touching, but we'll see if we can resolve that. So the simplest way to try to get these to be their own individual objects. So what we want to do is we want to assign an individual index, right, to every single pixel that belongs to the same object. So if this is object 1, we want this to be all 1s, and then if this is 2, we want this to be all 2. So the easiest way to do this is something called connective components. If you've ever used in Fiji, it's called analyze particles, that does connective components. And scikit-image can do this as well. So I think we already imported the library we need, which is measure. And so we're going to do that now to get the connective components. So our labels is going to equal measure. That's the module. And then label is the method. And what do we want to label? We want to use this foreground processed because it's definitely better than the raw threshold. So foreground processed. And this will do the work for us. And there it is. And now we can do viewer.add labels, and we can add the labels. And there we go. So now we see, I'm going to turn off these other layers. Now we see that every object has its own unique label. But we see that these three all have the same one, and these have the same one, and these have the same one. And that's because you can see that they're touching. So connective components make some assumptions based on pixels that are neighboring. And so it assumes that pixels that are neighboring are part of the same object, which is reasonable. And so what we need to do in order to fix this is we're going to need to separate these objects in some way. And there's a number of different ways that you can use to separate the objects, but we're going to do something called watershed segmentation. So the way that watershed segmentation works is that you can kind of imagine that these volumes that we see here are actually basins, and that you, from the bottom, you start filling them with water. And then you, as you fill the basin, before you start spilling over, that's when you have two separate objects. So you would fill this basin from the bottom. So in order to do that, we need to know where to start filling. And so traditionally, this is called a marker-based approach, where you would basically put a marker, a point in every single object that should be its own, should have its own basin. And so obviously we could actually do this in Napari pretty easily, which is kind of nice. But it can be a little tedious, right? So we could create a points layer, and we could manually mark the centroid of each of these objects, right? But then we would be doing this manually for everything, right? And so you want to kind of get away from doing things manually, because then it's not going to be very reproducible. It's time consuming. So we're going to want to find an automated way of doing that. So I'm going to delete this points layer. And let's take a screenshot of our cool, maybe in 3D, of our viewer. So we will use nbscreenshot viewer. And there we have our, so this is what our starting point is. And now we're going to do our segmentation. We're going to want to do the, we're going to want to divide this up using watershed. And so, like I said, the traditional way of doing this is to use a marker-based watershed, but we're going to want to compute the location of the markers automatically. And so one way we could do that is we could do something called a distance transform. And so what a distance transform does is it basically attempts to find the pixels that are the distance between an edge. And so when you do a distance transform, you will tend to reduce objects to something that kind of resembles like a skeleton a little bit. And so where the intensity will be the highest, that's the point that's furthest away from the edge. And so we could use that distance transform as the starting point for where to automatically put a marker. And so that's what we're going to do. And so we have a handy, we can do distance equals. And so we're going to use, in this case, this is a function, I'll just go back up here for a moment. nbimage is from SciPy. This is another, SciPy is another numerical library for doing all sorts of data analysis. And it includes this very handy module called nbimage. SciPy is pretty computationally efficient. A lot of the code is compiled in the back end, so it's pretty fast. And so we'll use nbimage, and nbimage has a number of different distance transform functions. But let's just use the EDT. I think I should be able to say EDT question mark. And here we have, so this is the Euclidean distance transform. And so it calculates the transform of the input by replacing the foreground elements with the shortest distance to the background. So again, it's going to basically, for every pixel, it's going to look at how far it is from the background, so from 0, and then that's what it's going to give us. So this is basically going to turn each of these into either a blob with a point in the middle, or into like a snake skeleton here, as this is elongated like this. So let's use that distance transform. This, using the question mark, is very, very handy, and I recommend you use it when you're working. I use it in Python all the time. It's hard to keep all of these things in your head, but here you can see that you need to provide an input array, and then there's some additional options that you can use in order to further manipulate the output. So we're going to calculate the distance transform of this foreground of the binary mask that we have. And then we can do viewer.add image distance to see what this distance transform really looks like. And so here's the distance transform as we have it. And let me go to 2D. It might be, and turn off some things. And so you start to see, if you look very carefully, let's see, change the brightness and contrast a little bit. You can see that there are some of these patterns in the signal now, where it's a little dimmer on the outside and then brighter in the middle. You can see that there's these projections between the two touching elements. You could see that there's clearly like a ridge line here. And so this is the information that's basically representing how far each pixel is away from the edge. And so if we look at that, and I'm just going to do continuous contrast here, if we look at that, we can basically, wherever it's the brightest, right? So the highest intensity, that pixel is the furthest away from the edge of the object. So that's probably the centroid, and approximately where we should put the marker for our marker-based watershed segmentation. And so we can do that. We could also blur this distance transform if we wanted. I think I do that in the materials. I think I apply a Gaussian blur to the distance transform. So we can do that here too. Basically, the idea of smoothing it is to get rid of the possibility that there's like two peaks, like, or two pixels that are like right next to each other that are bright and getting some sort of strange behavior. So we might as well follow along with the materials. But I think in this case, actually the data looks pretty clean, so we don't even think that we need to do it. We don't even need to do the smooth distance transform, but we can. So let's do smoothed. Just double check the chat. Okay, so we can do the smooth edt equals filters dot Gaussian. And then what are we going to smooth? The distance transform. So distance. We need to provide a sigma. And so we can provide a sigma of the distance, basically how far apart. We want to make sure that there's no markers that are closer than a certain distance. So maybe we'll do 5 here. That should be fine. And do we care about the preserving? I think we can go between 0 and 1 in this case. I don't think it really matters. So we can take a look at this. Viewer.add image smooth edt. And so there is our smooth distance transform. And so the goal of smoothing it is to try to have just one place that is the brightest in the object, such that we can place our marker there. And I think that probably this has accomplished that. So, well, we can take a look. We can try to use that as the location for the markers. So how can we place a point in the brightest spot in every single one of these blobs from the distance transform? We can we can get the local maximum, right? So we can, if we mouse over this, we see that, for example, here where my cursor is, it's about 9.8, and over here it's about 1.5. So if we follow the ridge up to the maximum, we're going to get a value somewhere around 9 point something. And that would probably be, that would be a good place to put a marker. So let's say peaks equals, and then this is from scikit-image from feature, and it's called peak local maximum. And again, the tab autocomplete helps a lot. And so we can, why don't we do the distance one first, the regular distance transform? So I will just do distance just to see what it looks like. And then how far apart? We can say how far apart we want the distances, the minimum distance to be. And so I don't think any of our points, any of our blobs are smaller than 10 pixels across. So if we say that we don't want anything closer than 10 pixels, I think that that should guarantee that we get 1 point per object, and that's our goal. Again, I'm not using the smooth one here just because I'm curious. In the materials, I use the smooth one, but I'm wondering if because we're using this limit of 10, maybe we can avoid using the smooth. And again, then we just save some computation. Um, and we can do exclude border equals false to not consider things that are on the very edge of the image, which would be difficult to analyze. So let's take a look at what that looks like. So we can compute that, but now we want to be able to look at where those peaks are. So we will do add points. And so we're going to add a points layer. And this is what I showed you doing manually, but we will do it automatically here. And so we can set the size of the points to say 5, and then I will do face color equals red so that we get some contrast between the and if you run this command, you might not see anything at first. But remember, if you're looking in 2D mode, you might be looking at just one slice. So hopefully the points are somewhere on other slices, and it does look like they are. Toggling to 3D, ooh, something is very unhappy here. Look at that. That is very bad. Something is not happy here. I wonder what just went wrong. Um, I'm not exactly sure, and I'm not going to worry about it right now. So there's some sort of points plane bug. This is probably an issue with, oh, I think I understand what could be happening. So I think it's because we have a mixture of different kind of layers, 2D and 3D. Wow, it's really unhappy. Um, let's try to go back to 2D and see if we can figure out why that was happening. Um, Huh. I'm not exactly sure why that was happening, but it was very unhappy about that. Um, it does look like overall, like if I'm just scrolling through it, that everything looks pretty good. And we can see. Thanks for saying, Angelo. You can see the materials, and you follow the materials. You can download the notebooks to run them yourself. So you can see that we do have 1 point per every object, so that's pretty good. So that's what we wanted. But why are we getting this crash when we go to 3D? I'm not sure. I'm actually gonna make a note of this. Oh, it's already here essentially. So I will come back to that. I'm just gonna scroll past all this error message. And I'm not gonna try to figure out why it's not working right now. It doesn't like something. There's probably something that's 2D and something that's 3D simultaneously. And we are getting, wow, this is a really long traceback. All right, scroll. Scroll. Jeezy crazy. Really amazing. Okay, so now I have my own um and I'm gonna clear out some of these extra layers. So we're going to get rid of the distance transform layers. We can keep the labels, just that, and then we have the points. I'm going to try it one more time. Oh, now it works. So one of those layers, I guess maybe was a 2D layer, and that's why. So there we go. That's much nicer. So we see that we have a point in every single object. This one here has 3. This cell is dividing, and obviously it's a bit of an outlier. You can see how it's labeled in 3 different places, but everything else looks pretty good. So we are not excluding on the border, but we could. So I think if we just change that, we could fix that. Do we want to try the smooth distance transform? I think this is good enough. Let's just skip that. we could do the same thing, right? The same thing that I just did. Obviously, I'd have to scroll all the way up. So if I scrolled all the way up, I could, or actually, wait, it's in the materials. If I go here and show you here, so here's our smooth transform. And here we could use the smooth transform, and we could calculate the peaks a second time using the smooth transform. And so actually, since I'm already here, I'm just going to be lazy, copy paste that. And so I will say use the smooth, but this time I'm going to say exclude on border true to get rid of the things on the border. So let's see what that looks like. Oh, did I get rid of smooth distance? Oh, I did. I called it something different. I called it smooth EDT. Nope, I didn't call it smooth EDT. What did I call it? Scroll up. Oh my gosh, this error is incredible. Wow, look at that. This is like the authentic experience right here. Smooth. I didn't use the past tense. Smooth EDT. So smooth EDT. Boom. And then viewer dot and points. Peak local max. Color equals blue. Or face color, sorry. Face color. Face color equals blue. Size equals 5. That seemed fine. And now we will have the points in blue that came from the smooth transform. And so, oh, that's interesting. So if we look at just the blue points, we did get rid of the ones on the items on the edge. We also got rid of this entirely. So that might actually be better, right? Because we probably don't know how to analyze this, and this is some sort of an outlier. So maybe that's fine. We can just ignore this. The other thing we could do is we could always go in here, and this is an napari layer. We could actually select this layer, and we could select the individual points, and we could delete this extra point, for example. Like we can just click on it and delete it. And so that's a nice thing is that like you can basically use some interactivity on top of what you have. But actually, these blue points look pretty good, so maybe we're just going to go with those and just try the smooth ones. Yeah, maybe. I guess when I wrote this, maybe I knew what I was writing about. I'm actually gonna put both of them up like this. That's kind of cool looking. And then I'm gonna say NB screenshot. Okay, so what we've done so far is we've done a couple different steps showing you how you can look at different kind of intermediate results. Again, we could be writing some comments here for ourselves in the markdown, and we could say, for example, the image below, shows in blue, but you see that right here. It says face color blue. It's the peak local max of the smooth EDT. I could have provided a name that would be more descriptive here, right? I could have said name equals smooth EDT or whatever. So that I really think in my experience, that's proven to be really powerful to be able to sort of document a process and be able to go back and explain why did I choose certain parameters? Why did I do certain things? Um, so I think that's really nice. Um, we are about an hour in. We're probably actually about 3/4 of the way through. So I think this is a good opportunity to stop for a moment and ask you guys what questions you have and whether there's anything that you want to catch up on or take a look at one more time or have re-explain. So please just feel free to unmute yourself or use the chat. This is a good point for any questions, comments, things like that. And if you're ready to finish out, then just put up the green check mark, and I know that we can move forward. And if you just need a break, if you just want a couple minutes, then put up the red X, and we will wait a couple minutes. That's also fine. If you want us to pause for a moment, that's fine. I've used it in the past. Yeah. So you can there's a couple different ways. The question in the chat is, do you use Stardust on Napari? So there's a couple different ways that you can use Stardust. Stardust is a Python package. So much like here, we imported filter, measure, morphology. We could have imported Stardust, and we could use the Stardust functions to use that machine learning model on our data. And so you can then provide the model. You can do whatever you want. You have full programmatic control of it. Stardust also has a plugin, or at least it used to. So you could also take a look at Stardust in the plugin finder. And there is Stardust Napari. So you could also install this plugin, and then you could have a GUI for using that, which would then allow you to apply the model to certain layers, depending on what the GUI permits. Typically, the GUIs in plugins are a little bit more limited than what you can do if you access them programmatically. Whichever way you choose to do. So again, in this example, I'm using the simplest, scikit-image. But everything that we've done thus far, we could have chosen to use Stardust instead. Typically with Stardust, you would also probably do some filtering. You might also want to exclude some objects on the edges. It's just that Stardust would take care of basically in an advanced way of choosing the right objects and separating them using a machine learning model rather than using classical approaches. But even with Stardust, there's a number of different parameters. There's the different size elements. There's you could choose different kinds of models. So Napari can be very, very useful for evaluating the output of a machine learning model because you can see by eye what how well does it segment? Where are the errors? And then Napari can be useful for generating training data. So you might need to train Stardust on your own data. And so then in Napari, you could create a labels layer instead of creating one programmatically like we did here. We could create one here, a labels layer, right? And then I could use the paintbrush and I could label this, and then I could change the label and label this. And this can be useful for training machine learning models on fine-tuning things like Stardust. Does that answer your question? I don't do science anymore. I help people do science. So, but I have used Stardust in the past. For the specific problem that I was looking at, I used Stardust and then I stopped using Stardust because Stardust was very good, but it was still significantly slower and used a lot more resources. And so what I ended up convincing myself is that I could get about 99% accuracy compared to Stardust using classical approach, using some filtering and thresholding. And so in that application, it made a lot of sense to do that. But in the write-up, this was actually the work of a student in a master's thesis. The student used Stardust as the gold standard. At the time, this was a couple years ago. It really was. And so instead of manually counting and segmenting things manually, we use Stardust as the gold standard. And so we basically tuned our manual our classical pipeline, our filter threshold pipeline, using Stardust as the true output. And when we got it to about 99%, it was good enough. But at the time, it was harder to access GPU resources, which really makes Stardust hum. So it made sense to do that. Very good question. So again, the same kind of work, like what you're seeing here, I've done with Stardust, but tuning different parameters of Stardust and trying to see what is the best way to apply it. And then instead of comparing, like peaks versus smooth or whatever, you would be comparing like two different Stardust models or a fine-tuned Stardust and whatnot. Okay. Let's Miriam, are you ready to go forward? Cool. All right. So let's finish some things here. Okay, so we have our markers. So now we need to do the watershed. To do the watershed, the way that scikit-image does this is it needs basically it needs the markers as an array. And so we have these points, which are kind of what we want, but not quite. Um, oh, by the way, the one thing I forgot to show. So if you're in 2D view and you can't see the points, you can try ticking out of slice. Um, and that might help. So that will basically consider the planes adjacent. So if the point is 5 pixels large, then out of slice will show the adjacent slices as well. The other thing you could do, this is new in Napari, is you could right click on the slider, and then you could get this is called thick slicing. So now we're basically averaging 10 planes forward and 10 planes back and displaying. And so with thick slicing, you're always looking at essentially an average over multiple planes, and that can be really useful for looking at things like points. And also just to give you a sense of what it looks like on the data. So now we're doing thick slicing. So you can see that it's kind of like a little bit blurred, but that's because every plane we're looking at is taking the 10 planes forward and the 10 planes back as it's rendering. And you can adjust how you want that to look. And then, of course, you can just fix it back to just one plane at a time or more planes averaged together. So this can be a pretty useful trick sometimes. Okay, let's do our watershed. So we want this markers array for the watershed. And there is a scikit-image utility function, which I use a lot actually, that will basically get you labels, basically an array from a set of point coordinates. And I'm going to do something different here. I'm going to show y'all how you can access data from the viewer. So we're going to, instead of passing here the peaks, right? So instead of using this, actually, maybe I should show you this first. So let's just take a quick look. So if I just print peaks, it was peak local max. So you can see that this is an array of coordinates. So the slice 35, x, y, x. So this is an array of coordinates. Um, and so, but this is the coordinates that we got from the output of this function. But what we could actually use instead is we could actually access the data of the viewer layer, of the layer in the viewer. So let's use the data of the layer. So now it's the data of the layer, and you see it's the same because we haven't manipulated the layer. But we could go in here and we could use the selection tool and we could find a point and then choose to delete it. Right. Wait, there was one on the edge somewhere. I remember seeing it. Or maybe we got rid of that. I guess we got rid of it. Um, but anyhow, or we could do something different. Like we could actually add a point. I'm going to add a point for that. Okay, so I've added a point that represents this dividing cell, and it's approximately in the middle, right? So I've added that point. So I'm going to now use this layer data specifically. So let's do our markers equals util. And I use this function a lot. It basically takes an array of coordinates and converts it into an array of like a 3D array, right? So viewer.layers peak local maximum dot data. So I'm taking the coordinates. I'm actually using the coordinates that are in the viewer. And then you have to provide the array shape that's the output. And so I want to provide an output shape, and I want to use the same shape as our image. So that's what I'm going to say. So I'm going to say, create me an array that is a binary mask that has these coordinates and is the shape that is this array. And you'll see if I do markers dot shape that it's the correct shape. And if I just print that array, that it's a bunch of zeros for the most part, right? But I can do viewer dot add labels markers, and I can check it out, see what it looks like. And you can see there it is. It might be hard to see, but there is a pixel, 1 pixel at every single, and in 3D, it's even harder to see, but maybe you can imagine, you can see them. Yeah, you see the little the pixels. So now we have converted our coordinates into an array that we can use for the watershed. And so we can use that watershed on this to break up these objects. So now we're going to do the segmentation using the watershed nuclei. So segment equals segmentation. That's the module from scikit-image. And then we will use watershed. Let's use the the distance transform again. And so we need to use the inverse of it because we want essentially negatives to be the basins. So smooth EDT. And then we want to use the markers. Actually, maybe I should do this again. Excuse me. So you see, we need to provide the image that we're going to segment, and then the markers. And then here's the connectivity, which is the, because we're doing connected components. So we want to provide the image that we're going to segment. And so that's the smooth distance transform. The smooth EDT, sorry. The markers, which is where our points are. That's what we just generated. And then the actual mask that we want to segment, which is the foreground processed. That's the name of the file. And so if we run this, we should be able to now look at this. Nuclei segment. Whoops. And there we go. And now if we zoom out, we should see the only ones we didn't separate are these right here. Why do we not see the points? Ah, there they are. Let's turn on the nuclei. And then we have our points. And then we need to reduce the opacity a little so we can see everything. It's still hard to see the blue. Maybe it's just the blue is hard to see, huh? So if we do on this layer, we should be able to do Control A, no. A. What does it say? Use Shift A to select all points in the layer. Yes, so let's do Shift A. And let's see if we change this to red, if it'll be more visible. It didn't work. Huh, wonder why not. Let's try again. So Shift A, and then we're going to make them red. Okay, and there we go. It worked. Okay. Thank you, Ryan. Again, hopefully you can follow along with the materials. So, oh, the opacity is low. Okay, there we go. Now we have the higher opacity. Boom. Okay, now we can see them. And then maybe I'll reduce the opacity of this a little bit. So we see that we didn't have a point for this one object over here for whatever reason. And so that's why these are still connected. But we could tweak we could tweak the parameters if we wanted still to get that point. I don't remember if I deleted a point somewhere. If that's the one I deleted, I know I added the one over here. This is also on the edge. So technically this should have been excluded. So that might be the reason why it's excluded. But now we can see that these guys, which we had connected before, so here's what we had before. They were all the same color. Now they are all separate. So we successfully did that. We can crank up the opacity. And if you're not convinced, you can hit this shuffle button, and then you'll see that they change color. So that means that each of them is their own object. So I want to, so basically we have completed, so let's do a nb screenshot to take a record of that. So we have completed the segmentation, but I want to show you guys one other thing that I find really useful in Napari to be able to visualize some measurements. So basically, to be able to look at measurements here in the viewer and to get a sense, for example, create something like a heat map, things like that. So we still have a little bit of time. So we will let's give that a shot. And so scikit-image has a fantastic function called region props. So let's create a table, and we will use this region props. Region props. So here's the region props, the information about it, and so here's just some of the things that you can access. So you can get the area for that's for 2D. If it's a 3D image, it'll give you the volume. You can get the major length, the minor length, the bounding box, the centroid location, the intensity, the image intensity inside the region. You can get the mean intensity inside the region. You can get a whole bunch of these other parameters that I'm not sure what these moments are. You can get some solidities. You can get some perimeters, which is the basically the outside. So there's a whole bunch of these really handy different parameters that we can calculate. And I'm going to use the table option, which basically will use those properties but return them as a pandas compatible table. And if you're not familiar, pandas is a data frame library. You can think of pandas kind of like Excel. So basically it lets you work with not arrays like NumPy, but work in column-based tables. And so we're going to use this approach to get some measurements. So we need to be able to look at two things. We need to provide the label image. So that is the image that provides a number for each object. And then the intensity image, which is optional. And the intensity image is the image where we want the measurements from. So in our case, that's nuclei. So let's do that. So the label image that we have is called, I've already forgotten, nuclei segment. And the intensity image in our case is just nuclei. I don't remember if this needs to be intensity image equals nuclei. That's the actual data. And then we can pick some properties. So I have a few of these properties memorized. So I will use a few. So we can get the label itself just as a sanity check. So that's the number. We can get the number back, which is handy in a table. So let's get that. Let's get the volume, which for 3D objects is scikit-image still calls area. It's unfortunate, but it does. And let's get the mean intensity of these nuclei. Intensity. And let's get something called solidity. I don't remember exactly what this does. Solidity. So there you could add as many different properties as you want. There's ways you can provide your own custom properties if you would like. So let's just see what that does. So we're computing these different features for each one of our objects. So it could take a moment. And then this is the nice thing about Jupyter is we can just print. Oh, didn't actually print as nicely as I thought it would. I was kind of expecting to get a nice table printed here. But you can see that we now have this list of the indexes, and then here's the different volumes of the objects, and then here's the mean intensities, and then here's the solidities. Why type? Why is this not actually a pandas data frame? I kind of thought it would be a data frame. Data frames usually print much nicer. Let me just take a look. What does this return? What does this return? So it returns. Here's the parameters. It returns a dictionary. Oh, okay. So it returns a dictionary, not a data frame. That's my bad. But there's a way to get a data frame, and right, we could import pandas, and then we could get a data frame out of it. So we might want to do that. Probably doesn't matter. I think we could skip it. Okay, so let's say that we want to now take a look at these objects, but we want to color them by some parameter. So let's say we want to color them by their volume, which again, in terms of the data frame, is called the area. So let's do volume. And then we need to use and then we want to color them by the volumes, and we're going to use a color map. So color map is the representation that we're going to use for the shade of the color versus the value. So I'm going to use the varieties. It's a pretty common heat map style. And so from napari.utils dot color maps, import ensure color map. And so this is just a utility function that will make sure that we can actually grab the color map that Napari uses. So varieties is going to equal ensure color map. And then varieties, that's the name. And so now I should have the actual color map. And this is each of these is its own color. This is the array. So each row here is the RGB values essentially of this color map that give this characteristic yellow to green look. And so now we can create something called volume colors. And so we're going to take the varieties color map and then we're going to map it onto the values from our table. So basically, let's do this normalized. So that means we're going to take the info table and we're going to grab the area. So we had that up here a moment ago, right? Area. So we're going to take the area and then we're going to normalize the areas of the nuclei by the maximum area. So that's the area. This is the area of any individual element, and then we're going to normalize by the max. So we're going to get the largest nuclei is going to get a value of 1, and then proportionally the other ones will get a smaller value. And then we can add this. We can apply this as the color map to our label layer here. So we can convert that here. So let's do that. So we say viewer.layers. What's the name of the layer? Nuclei segment. Nuclei segment. Okay. And then we want to change the color map to use this color map that we just computed. And if we do that, we now have a heat map basically where the objects that are colored based on the normalized size. So they're no longer colored randomly like we had before, where each one was just its own color. This is now essentially a heat map where each object is colored by the normalized size. So that's a pretty handy trick that can sometimes be useful to be able to use the labels layer to visualize something. You can also map them onto the labels. There's a lot of different ways that you could do this. The other thing that we could do is we could also basically encode the properties that we have as so-called features of our layer. So let's see how that works. So we say viewer.layers, nuclei segment dot features. This is a property of our layer, and we're going to pass here the info table. And so what Napari is going to do is it's going to take that table that we have and associate it with each of the objects. So let's see what that looks like. Viewer.layers, nuclei segment dot features. And so now we have this data frame where we have each of our objects. It has its own label. And here's the area and the intensity and the solidity. And these features, so these are basically now associated with the layer. And the cool thing is in Napari, there's now a feature table. So if you go to layers, visualize, you can open the feature table widget, and we can make this a little bit bigger. And so here is our table. And when I click on these, you don't really see anything happening. But if I say show selected, so this is the labels layer, and I'm asking it to only show me selected. Then as I click on the different rows of my table, you see that the individual nuclei gets highlighted. So if I sort this by solidity, and I want the highest, the most solid nuclei, it's this one. If I want the least solid nuclei, it's that one. Which is the biggest? This one is the biggest. Really? That one looks kind of small to me. I thought that one would be a small one. Oh, maybe not. I guess it's kind of prominent. So what's the smallest one? It's this one. Its neighbor over here is actually the smallest. Huh. That's interesting. This one to me looks bigger than that one. But maybe they're not, maybe it's the difference in the heights. Huh. Interesting. But you see how this is working, right? So basically, this table permits you to interactively explore the data. And if you instead leave all of them, you can do this in the opposite direction. So which is this one, this yellow one? We can use the picker to select this label, and then it should, oh, it didn't work. Huh, interesting. So I would have expected it to be selected here, but it's not. But this is, so if I don't do that, right? If I hover over, oh, it doesn't have any properties. Look at that, number 16 down here at the bottom. If you look down here at the bottom, as I mouse over these, you see the properties. But the 16th one doesn't have any properties. So it wasn't able to compute, probably because of this odd shape or something. But we have a 16th label. Huh. But which one is it? It didn't work. Interesting. So that seems like a bug. Why is this one not working? It's showing that one. Huh. I'm not sure why that's the case. Oh, because here's 0, right? That's the background, and that's 15. So this 16th one is, oh, I know what happened. So what happened is when I generated the table here, sorry, here. Look, I used the nuclei segment. Oh, but that should include that. But there's only 16 labels here. Yeah, that's 16 labels. This is number 16. So I'm not sure actually why that's not working. So somehow it wasn't able to compute properties for that. Napari is somehow not handling the properties for this strange object very well. Yeah, I'm not sure exactly why that is. I'll try to look into it after the after this workshop. But that's everything I had. But you can play around with these different ways to visualize your data and different ways to interact with it using this approach of basically here's in the materials. You can take a look at what I wrote here. Um, yeah, so you can generate these different kind of visualizations, which basically rely on computing something, and then, in this case, we're normalizing the data based on that. So you have some options here for these kinds of displays. So that's a quick way of generating something like a heat map. And then this features table is a pretty new thing, but I've definitely found it to be pretty handy in the past. And yeah, I guess this one's the biggest, huh? Interesting. It doesn't really seem that big, but I guess it is. But I don't understand why that last one isn't included in the thing. So I'm happy to answer any questions. Any questions related to what we just covered, or any questions related to Napari. There's still we're done a bit early. There's about 15 minutes left. So I'm happy to hang out and answer any questions, or provide any feedback, or whatever you might want or need. I'm gonna stop. I guess maybe I keep the sharing in case you have some questions. Then I can point to those as well. if you're interested in the features, if you go to this other one, exploratory analysis optional, this is a different thing. It does some spot detection. This is basically like a RNA assay. But at the very end, we use the features in a different way. So we generate some points to locate our spots, and then we color the points based off of the intensity of the spots. So I think this is a pretty cool example too of how to use the features to be able to basically color things or interact with them. So we compute something using, in this case, we just get the intensities, and then we use those computed parameters for each of the points. Any questions, comments, concerns? Cool. Glad to hear. We're done. So if you want to drop, you can drop. If you want to hang out for a bit, or if you have some questions, please feel free. If you're finishing something and you want to finish it, how do you create a selection in 3D? So in 3D, what kind of what do you want to what are you trying to select, Miriam? Are you trying to select um because like in this case, I can select the individual like I can select the individual labels by clicking on them, and you see that they are selected in the table. For points, I'm going to just close the table and hide this. Um, Points are a little bit better. You can use the selection tool, and this usually works in 3D. So you can select points like this in 3D, um, but not always. It's kind of tricky to modify a previous selection, for example. Um, Niels, your question about yeah, let's see here. So to modify a previous selection, for example, Miriam, do you want to maybe, oh, I guess you can't probably. What do you mean by previous selection? Um, oh, you mean like if you wanted to modify like this? Like if you wanted to modify like the, okay, so you can actually do this in 3D. There are the paintbrush and the eraser tool work in 3D, but they are, so I'm going to just show this real quick. I'm going to duplicate this layer, um, and then I'm going to just turn this back to the uh, oh, I just messed that up. Okay, I wanted the eraser tool. So basically, you have two options. So let's say we want to separate these two, right? So option one would be to use the eraser, boom, and then just change the brush size, right? And then you could just erase between the two. Oh, that didn't really work, did it? I suspect this is what we should be doing. I think because I messed with the color map, that things are going to be yeah, because I changed the color map. I don't think I really wanted to do that. Um, but you can use the eraser to do that. So that's option one. But then you'd have to do it on every single slice, right? So you'd have to erase here, right? And so on and so forth. So if you over here, if you do edit 3D, you can edit in 3 dimensions. And then what you can do is you can paint here, but you're actually painting with a ball instead of a circle. And so if you do that, it should be possible. You can see that I have essentially changed that a little bit. Um, and you can use that also in 3D. So you can see that you can paint, but it's tricky because like it's a 3D object, right? So like I find painting in 3D really difficult to follow. And so I tend to use I tend to use the 3D edit mode, but I tend to just use it in 2D. And so if I do that, I have almost separated those objects. Uh, so that's always an option. What we did here, right? We used a programmatic way of separating the objects. And so I would encourage, what we should do is adjust the parameters of what we did in our notebook to get the better segmentation where the two objects are well segmented automatically rather than doing it manually. Niels, your question about functionality related to Fiji. So I would say that Fiji and Napari are not very similar at all. Napari is just a viewer, right? So it's a way to look at images. It has this model of layers that allow you to look at things one on top of the other. Fiji generates one new window for every single thing you do, so you have a ton of separate windows. Napari is a Python application, so I find like I like Python and I use Python. So using this notebook and interacting with Napari, I think is really great. And I don't think that there's a way of doing something like a notebook for Fiji. Uh, Fiji has a ton of different plugins and has been around for like I used it in grad school and even which was I got my that would have been 25 years ago. And Napari is only like 6 years old, so Napari is a lot younger. Um, and while we do have a lot of plugins, there's not nearly as many options for Napari as for Fiji. Um, what other differences are there? Yeah, Fiji's in Java, so in some regards that's easier, and but in other regards it's not so great. When I was using Fiji, I never really got things like Stardust and Cellpose to work in Fiji, but in Python I've been able to get them to work. You can install, Stardust as a library, and then you can access it in a notebook. You can install it as a plugin, and sometimes that works depending on your data. So. I wouldn't say they're very similar at all. I would say they're quite significantly different, like depending on what you're trying to do. Napari really is sort of more for viewing images and for facilitating this kind of interactive analysis. But at the end of the day, you're going to get a table of numbers somewhere, right? And then you're going to publish a paper that says, when I treated my cells with drug A, the average solidity of the nuclei was lower than with when I treated them with drug B. Um, and Fiji has a lot more stuff built in. So I don't know if that answers your question very well. Um, you can certainly use them for similar things, but I think that they have a totally different approach in how they work. Any other questions? Fiji is great. I mean, I use it. A lot of people at my work use. I just find this kind of ability to use the notebooks and where we could create here a notebook cell, and we could say markdown, and say we did a nice job, and then you can go back to this notebook and then you'll have all those answers in it. I can show you, like I have I can show you the notebooks that I prepared, right? So here's this is the same notebook, right? This is the one that let me see, just open with notebook. Um, so this is the one that I wrote, and so you can see I went through the same process, through the same analysis, but I wrote a lot more information. And it ends up being you can run this yourself to see it again. Um, there is this library, yeah, there is a library called Napari Image J to use them together. I've never used that. I'm not sure how useful it is. Like, I find that like something like watershed segmentation, like that's a standard algorithm, or Otsu threshold is a standard algorithm. It's like, why would I want to use the Fiji version in Python? Or in Fiji, why would I want to use the Python version of Otsu segmentation? But I'm sure people do use that package. I think it's actually a plugin. Let's see, ImageJ. Yeah, ImageJ functionality from Napari. Um, so this is kind of nice. I've used this before, actually, the ROI manager. So if you have generated ROIs in Fiji and you want to look at them in Napari, then this works. I think it just depends on what you're used to and what works for you. Um, One of the motivators for me was this ability to look at things like this, to be able to do these kinds of like overlays of a lot of different things. And Fiji doesn't have that. Um, Yeah, so Fiji by default has bioformats, which opens a lot of different things. In Python, bioformats is a Java library, so you can install it, but it's a little annoying to install in Python. But there certainly are a lot of different libraries in Python for reading a lot of different things, but maybe not all in one place like bioformats. But you certainly can install bioformats and use bioformats from within Python, but it is a little awkward because it's Java and Python doesn't have that. Um, most of what I use is I use the TIFF file though that for the things that I have. But that's a really good point. Fiji definitely has the ability to open more things out of the box. Napari has some, it can open files out of the box, but a pretty limited subset. Like we don't include like every possible reader that you would need. And so you can install readers that will open things out of the box. But you can also, if we go back to the beginning here, um, if we go back to the very beginning here, we can basically if you can write the code to load it, I had it somewhere. Learning Napari. Maybe it was here. Uh, yeah. So if you can write some Python to load the image, then you can always use that. So um, yeah, I don't think it's like one or the other. It just depends on what you prefer to use. Kind of like some people like to use Windows and some people like to use Macintosh and other people like to use Linux. Like I think that you can do mostly all the same things, but you will do those same things in slightly different ways. So in Linux, you might use the command line more. In Windows, you might use Microsoft things more, and in Mac OS, you might use Apple things more. But like at the end of the day, if you want to write someone a letter, an email, or write a publication, like you're going to use more or less similar things in different ways to get the same outputs. So I think that the two are very, yeah, very similar in some ways, but very different because you don't have all the windows. So one of the things I never liked about Fiji was that you would have so many different windows. If you tried to do something like this, you'd have like 15 windows floating all around your screen. So any other questions, comments? We have just a couple more minutes left. So I'm going to give you guys just one more resource, napari.org. If you go to napari.org, you can find you can find some additional tutorials under the usage. So there's some different tutorials here that might be interesting for you. You can find some additional information about the viewer and some new features that I didn't show and talk about. The viewer tutorial has some information. Then if, from this website, you can access the Napari Hub, and this is where you can search for different plugins. So let's say I wanted a plugin for I don't know, glyphs. It's a Leica format. Um, So there's something called BioIO Reader, BFIO. Oh, this is bioformats. So you were saying that you were using BG to open things. So this BFIO is bioformats. So this is a Python implementation of bioformats. Um, Again, these plugins are not made by me or any of the Napari team. They're provided by the community. Just like Fiji also has a lot of format. How well does Napari perform with huge files? So it depends on the kind of file. So I can show you real quick. Um, it depends on the kind of file. So, for example, the kind of files that I work with most commonly are pyramidal. So they're like from a slide scan. You know, from a slide scanner. And so I just have I have an example. And so they're probably about like 40 gigabytes uncompressed, maybe 60 gigabytes uncompressed. So I have just one, this is like a sample file. So, uh, So if you have a pyramidal file, I can't find it. So if you have one of these pyramidal images, um, then then Napari will load the pyramids, and it behaves quite similar if you've ever used QPAP, where as you load, it will load the next levels. Um, we have a problem here, but that's actually not related to. Yeah, I need to set. There's a setting here called render asynchronously, which helps with this kind of performance. Um, so then you're basically, as you zoom, you will render the different areas. This plugin that I'm using is something, it's a little bit experimental. I'm just using it as an example. There is some fixes that still need to be applied to improve the performance for these strange Hamamatsu files, which have the wrong sort of tiles inside. Um, but for these kinds of large 2D images, I think the performance is pretty good, as long as you have pyramids. If you don't have pyramids, then the image doesn't fit in memory. And then everything you do here, this canvas, this is sent to your GPU using OpenGL. So a 40 gigabyte file is not going to fit on your GPU memory unless you have like an A100, NVIDIA A100 or something. So what Napari does is it will only send a portion of the image to the GPU. And so for large 2D images, the pyramidal approach works really, really well, I think, and it's quite performant. Um, OME ZARs and things like that are sort of the ideal way to handle those kinds of large files. But if you have very large 3D images, like confocals that are like 10,000 by 10,000 by 10,000 or something like that, then unfortunately Napari doesn't handle them very well because of the fact that there is something called a texture limit, and most GPUs can only render things of a certain size in 3D. Um, and the problem is that Napari downsamples to fit into that texture limit rather than basically showing you just a piece of the image in high resolution. So that's a limitation that we're still working on. So if you have large 3D images that are more than say 5,000 pixels aside, then the performance isn't great. But I suspect that most viewers will have performance issues with that. And Fiji certainly can't open something that's that big because of the fact that Java has a limitation on how big of a image it can display. So for large 2D images, I think the performance is pretty good. For large 3D images, it's not great. And then I would probably suggest looking for something like NeuralGlancer or something like that. Um, there's something similar like Big Data Viewer. Um, yeah, so Big Data Viewer is Yeah, I've never really used Big Data Viewer all that much. I think if I know correctly, Big Data Viewer does this thing where it will show you, like, as you rotate the 3D image, it shows you like high resolution in the front and low resolution in the back. And that's the thing that Napari does not do. So the Napari will try to render everything, and then it can't render everything because the GPU can't handle it. So, um, so if you have very large 3D volumes, it's not the right tool. Um, oh, and I want to show you guys one other thing. If you go back to the Napari webpage, where is it? Oh, here, community chat. So we have a Zulip channel, and so these kinds of questions that you're asking right now are perfectly good things to you're probably seeing some of my private channels as well, because I'm logged in as me. But please just, if you see anything pop up, just ignore it. But here's, the general chat. You can just ask some questions. So Napari inside Fiji, somebody was just talking about this. There's all sorts of different topics. This is a good place. And then of course the ImageSC forums are the other good place. So I highly recommend if you have questions that are sort of Napari specific, maybe not image analysis specific, but Napari specific, then the Zulip chat can be very good for that. If you're running into problems, like you have a crash or a bug, then Napari Zulip is really good for that. If you're having questions about like, how do I analyze this problem? Or how do I migrate my workflow? Then those are better for ImageSC because they're like a broader topic for discussion. Any other questions or comments? we're basically at time now, so we should wrap up. So I'm going to stop sharing. Oh, my camera died. I didn't even realize that. My camera is problematic. It doesn't like being on very long, so it just kills itself randomly. Yeah. Any other questions, comments before we finish? Thanks for using the emoji. That's great. Miriam, any questions, comments? All right, no questions. Cool. Okay, well, thank you both for sticking through the bitter end. It's hopefully that was useful. If you have any questions, feel free to reach out to me on Zulip or on ImageSC forums. And you have links to the materials. So please enjoy. And yeah, hopefully that was useful. Feel free to share those materials with your colleagues or friends or whatever. It's all available. So have a nice one. Cheers.